So in this video, we're going to talk about how we can produce a bent piece of metal that looks something like this from a flat piece of metal, which looks something like that. And we're going to go through the niceties and intricacies of doing this on the press brake using what's called air bending. So the first thing to note is that this particular shape isn't actually realizable. There'll always be some kind of radius on both the inside and the outside, and the radius that we're going to end up with depends on the choice of tooling that we use. So what we're going to do is we're going to annotate this, show all of the key parameters, and then we're going to derive the formula which will let us compute the length of the flat piece that we need to bend into a particular piece here with some particular geometry. So if we take our annotated drawing here, so we'll always work with the outside dimensions, because if you've got a complicated bend, it might not be possible to measure the inside dimensions, and it makes the maths easier. So here's an L piece, and we want to go on to width of this length here. We measure to this imaginary point here, which is often called the mould point in the textbooks. And then we've got a height we've got here. There's an angle that we want to bend. And then, as I mentioned before, there's this inside radius, which, depending on what we're making, may or may not be critical. But we've only got a few finite choices of this, depending on the tooling anyway. So I just want to emphasize what the mould point is. So this dimension from here to here, h as is shown, we could measure that with depending on the size, a big pair of calipers, or a tape measure or something, or a height gauge, and this one. But the inside measurement, as I said, can be harder to measure. And then there's the material thickness as well. So the combination of the choice of material thickness and the tooling, which will affect the inside radius, affects the inside radius. So let's get on with deriving it. So this is the same drawing I just showed previously, but we've got some more annotation. So the strategy is going to be to compute this value here and here, which is the offset in each axis, called the setback. We're going to subtract that from h, subtract that from w, and then add in some material to account for the fact that there's a curve here. So the first thing to note is that this is a radius, and a radius will have an origin, a center. So we can think of a circle, my very badly drawn circle here, that goes around here. So we can probably, for 90 degrees, we can easily see what the setback value will be if we pretend that I've drawn this properly. We've got one here to here. Then we should be able to tell that if we know the radius of this circle, that's r, then you can see that this setback, and that's r as well obviously, that this setback is r plus the material thickness. So for this 90 degree case, the distance from here, this one, all the way out to here is r plus the material thickness t. And similarly, because it's 90 degrees, this one here is r plus t. So this one is r plus t as well. So for the 90 degree case, we can say that the setback is r plus t. Now, what happens if this angle was not 90 degrees? That's the next thing to consider. So what about when the angle isn't 90 degrees? So I've actually drawn this as 100 degrees here. So one side of this triangle is still the radius plus the material thickness, but the other side is no longer equal to that. So we have to compute this based on what we know. So we know that this angle here is half of this angle, because we're assuming that half of the material goes into that side of the bend and half of the material goes into this side of the bend, and we're going to bend it in the middle. So we can use the basic rules of right angle triangles. So we know that for this particular triangle, where this angle is theta over 2, so we know that tan theta over 2 is equal to the opposite over the adjacent. And in our case, I'll write this a bit more neatly. The opposite is the setback, and the adjacent is r plus t. Therefore, we know that the setback is r plus t times tan theta over 2. And we should be able to see from symmetry that this, I can't draw this very well, but this other distance here, this setback from this one, from the mould point to where the curve starts, this setback, and this is r plus t as well, because that's the radius, so this setback is exactly the same as this setback. So we know that our setback formula in each dimension is just given by this, which gives us the number that we need to subtract. So don't forget that this whole side here, draw this properly, this is h, and then this is w from the mould point all the way to the end. So we know that what we've got to do is do our flat length is going to be h plus w minus 2 times the setback plus some material, some length to allow for this material that's going to be stretched around the bend. So plus something, and that's normally called the bend allowance. Just to write that out, h plus w minus 2 times r plus t tan theta over 2 plus bend allowance. Just to make that a bit more readable, this is where we are so far. So we've got our outside dimensions h and w. We subtract the setback, and then we have to add in the bend allowance, which we haven't computed yet. So the bend allowance is very simple. It's just the length of the arc along what's called the neutral axis, which, depending on the material that you're bending, will occur at different points on the metal. So when you bend this, the outside here stretches and the inside compresses, but there'll be a point some distance measured from the inside, which is between 0 and 1. So if you were here, you'd be right on the inside, and here on the outside. So that's k, between 0 and 1. And then it's just the length of that arc. So we know that arc length is just the radius, some radius, times the angle in radians. I can write properly. So the question is, at what radius does this arc come out? Now that depends on the material and the particular batch of the material and all sorts of strange factors. But for steel, 2mm steel anyway, that I get from the laser cutter, I've found that k is approximately equal to 0.4. So the length of this arc, if we're going to call that, where shall I write it? Write it here. Arc length, which is the bend allowance, is theta divided by 360 times 2 pi times the radius, and the radius is the inside radius plus some factor k times t. So t is the thickness, so we have to come out to here. So whatever fraction of t we are away from that, and that's the radius that is from the origin of that curve. So that then gives us our final formula, which I shall show on the next slide. So here's the final formula for an angle theta, 90 degrees or greater. This line represents a setback, this line represents the bend allowance, which I did draw it in a different colour, but only printed in black and white. And that's the formula. Now, we should be able to see that this will reduce a bit if we're bending for 90 degrees, because we know that these will evaluate to something nice. So so for theta is equal to 90 degrees, that's equivalent to pi over 2, and then tan of pi over 2 is just 1. So that leaves us with our flat length, I think I called it L on an earlier slide, is h plus w minus 2r plus t plus r plus kt, and that'll just be pi over 2, which is about 1.5, isn't it? Because I'm assuming that the angle was in radians. And that's how you compute the flat length. So the things we have to decide as the fabricator are r, the inside radius, and k, the so-called k factor, which depends on our material. And for the purposes of the demonstration that I'm doing here, we're going to use 0.4. One more thing before we do the worked example. I want to talk about how you calculate the internal radius of the part. And this is defined, when you're doing this kind of air bending, by the width of the V. So this is a bottom tool, and we'll see it when we go to the press brake in a minute. This can be mounted so that you can use one of any of these 4 V's, and the key parameter is their width. So this top one, this is 16 millimeters wide. This one's 22 millimeters wide. I think this one's 35, and this one's 50. So for thicker material, you kind of have to use a wider V, otherwise you end up crushing and damaging the material. But for what we're doing, which is 2 millimeters, we're going to use the 16 millimeter V. And there's a very effective rule for computing what the internal radius will be based on the V width, and that is that the V width divided by 6 is the internal radius. So we'll just write that down here. So R equals V width over 6. And I found this to hold for all the sizes on this standard V. So the V width that I've got, and is very standard, is 16, 22, 35 and 50. So you can see that if you increase the width, you get a bigger radius. So for the one we're going to do today, we're going to use 16 millimeters. So 16 over 6 is 2.67. Sometimes for 2 millimeters I also use the 22 millimeters, and 22 over 6 is 3.67. So this is the inside radius, and then it should be fairly obvious from the drawings we've already done that the outside radius is just this plus the material thickness. The final point about the top tool So this has a radius of about 0.8 millimeters on it, and bending up to about 8 millimeter steel, I found that it doesn't really matter. This doesn't impact your calculations at all. When you get to when you want really big radii and things that aren't normal, then this starts to have an effect. But the top tool has more of an impact when you're making complex shapes and parts bend round and hit it. So this is a gooseneck tool, so you can have some folding back, but straight tools are also useful, and you can get all sorts of elaborate shapes with holes in them, etc. Okay, so now we're going to do a worked example of a 90-degree bend, and I'm going to make up some numbers for our purpose of our example. So we want to make a piece in 2 millimeter steel, where this dimension is 100, remember outside dimensions, so the imaginary mold point, and this dimension is 143.9. So what we need to do is work out the length of the flat piece, get that ordered, which will happen magically because this is a video, and then we need to work out the point that we're going to bend it at. So what do we do here? So we've got h equals 100. Need to keep this square on for the camera. H is 100, W is 143.9. R, we're going to use the 16 millimeter V, so R is 2.67. The material thickness is 2, and the K factor that we're going to use is 0.4. So if you work this out, flat length is 243.9 minus 2 times 4.67 plus 1.57, that's pi over 2, times is 3.47. Okay, so we can work all that out, which I'm going to do on the calculator shamelessly. And all of that works out to be 240.0079. So we'll call that 240 millimeters. So we need a flat piece of steel that is 2 millimeters thick and 240 millimeters that way. And then the other dimension, the dimension into the page, doesn't really matter for the purposes of this example, but it does affect the bending depth parameter on the press brake. So I think the piece that we're going to be using today, the dimension into the page is 80 millimeters, although that doesn't affect any of the calculations we're doing here. So we know the length. Now we need to know the point where we bend it. So we've got our flat piece of steel. We've got our two things here. So we've got h minus the setback, which is this distance. And then we've got w minus the setback, which is this distance. And then we've got here, which is the bend allowance. And we want to bend right in the middle. So that whole thing is the bend allowance, which is this term. So obviously, assuming we're bending in the middle, the position that we want to bend at, which is the setting for the backstop on the press, so we're going to call that backstop, is W minus SB plus BA over 2. And that I'm going to work out on my calculator equals 143.9 minus 4.67 plus 2.72 is equal to 141.95. So that's the distance if we're going to bend from this side. Similarly, we could equally, for this particular part, it's just such a simple bend, we could bend from this side. So the backstop would be H minus SB plus BA over 2 is 100 minus the setback, which is 4.67 plus 2.72, it's going to be about 98, isn't it? 100 minus 4.67 plus 2.72 is 98.05. So we can bend from that end or bend from that end. So let's take our blank down to the workshop and give it a bend. Okay, so we've got the press brake set up using the 16mm V. Should give us an inside radius of 2.67mm. We're going to bend this 240mm long flat, and our target dimensions are a vertical of 143.9 and a horizontal of exactly 100. So I've already set the press up to give us a angle of 90 degrees when we bend it, which is a different topic. Hopefully if you've got a CNC press, that'll be easier for you. So there we are, we're all lined up, and let's bend it. Well, it looks pretty good. We'll test it on the flat plate in a moment. Let's go over to the flat plate. Okay, so here we are at the flat plate, surface plate, and we're going to measure the part that we just bent. So first of all, we'll just check it for squareness. Well, it's pretty square, but it's not perfect. I could probably have, it's probably overbent. Ever so slightly. I probably could have knocked another 0.05mm off the bending depth, but it's good enough. Right, so now we're going to measure the height. So according to the drawing and the calculations we did upstairs, the vertical height here should be 143.9. So let's go. I'm going to have to adjust the camera angle. Or measure it in the middle first, and then we'll see how square the bend was. Oh! Oh! Well, that was surprisingly accurate. 143.89. Let's see how it varies. Zoom in a bit. See that? Yeah. Let's see how it varies if I... Yeah, so it wasn't quite perfectly square. The backstop on the press isn't perfectly square. So 143.93, 143.87, and 143.86. So that's not bad. Now, if all the calculations are correct, the other flange should measure pretty much exactly 100mm. So just the shot slightly. So I've turned it around. That's the other flange. Hopefully it'll come into shot. I'm going to have to bring it up. Right, here we go. Oh, 100.02. It's pretty accurate. 99.91. So it looks like we are 100.02. We're about 0.1mm out, which isn't terrible. But it does show that the K factor is about right. I suspect the sources of error are most likely the backstop accuracy on the press. Also on the, you sometimes get artifacts from the laser cutting. So if there are any artifacts on this edge, that can affect it as well. So there we are, we've bent this 240mm long plate into a flange length of exactly 100 and the other flange of 143.9, all plus or minus 0.1mm. which is reasonably satisfying.